Hi everyone, our ICRA 2020 presentation topic is on experimental comparison of decentralized task allocation algorithms under imperfect communication. My name is Sharan Nayak and I'm representing the other authors mentioned here, and we are from the James Clark School of Engineering in the University of Maryland at College Park, USA. And our work has already appeared in the IEEE Robotics and Automation Letters Journal in the April issue. Teams of UAVs need to communicate in order to perform the task allocation process and then verify task completion. However, in the real world, wireless communication is often unreliable due to fading, path loss, and other issues which can impact the task allocation process. There are two major paradigms for task allocation. The first one is centralized, where there is a single master who coordinates the task allocation among the other agents. The next is we have decentralized paradigm where all agents equally participate in the task allocation process. The comparison of centralized algorithms under imperfect communication has already been studied by Oti et al. However, little work has been done on the comparison of decentralized task allocation algorithms under imperfect communication, which our work seeks to address. The main motivation behind our study was we wanted to look at how the performance of decentralized task allocation algorithms decreases when the communication level decreases. As an example, consider this instance where we have 4 agents, A1 to A4, and they're using a simple task allocation, decentralized task allocation algorithm to visit all the 4 targets T1 to T4. In the ideal world, in assuming perfect communication, the agents simply would have collaborated and visited all the targets. However, because we have lossy communication here, we have agents A1 and A4 visiting the same target T2 and target T4 not being visited. So the main contribution of our work is the systematic comparison of 5 decentralized task allocation algorithms across 3 communication models and using 2 scenarios. The task allocation algorithms we consider are CBAA, ACBBA, DHBA, HIPC, and PI. The 3 communication models we use are the Bernoulli model, Gilbert-Elliott model, and the Rayleigh-Fading model. The 2 scenarios we use are the collaborative visit and the collaborative search and visit. And the 2 performance measures that we include in our comparison are the max distance traveled and the maximum messages transmitted. We now move on to the 2 scenarios. The first one is the collaborative visit scenario. So in this scenario, agents know about the location of the targets at the start of the simulation. So agents simply use a decentralized task allocation algorithm to collaborate and visit the different targets. The next is the more interesting one, which is the search and visit scenario. And in this, agents collaboratively visit and search and visit unknown stationary targets. And to facilitate searching, we have divided the workspace into a set of 5 by 5 grid cells. So the agent visits 6 grid cells and upon visiting them, sends the targets and then collaborate to decide which targets and which grid cells to attend. We next move on to the decentralized task allocation algorithms. So all of these algorithms vary in their task assignment type. Some use a single task assignment, others use multiple, while as like the HIPC algorithm uses a full task assignment. In terms of the data exchange, some use bid list, while algorithm like DHBA uses cost matrix and PI uses significance list. In terms of bid determination and task assignment, CBAA and ACBBA uses auction, DHBA uses a decentralized Hungarian, HIPC uses a full task allocation algorithm, whereas PI uses something known as significance for the bid determination. So in terms of the communication models, the first one is the Bernoulli. This simply consists of a single parameter P, which is the probability that the message sent by an agent is successfully received by another agent. The next is the Gilbert-Elliott model, which consists of 2 states. The good state represented by G here and the bad state represented by B here. So the good state has perfect communication and the bad state has 0 communication. And we have state transition probabilities that provide the probabilities for the transition between the good state and the bad state and vice versa. Finally, we have the Rayleigh fading model. It consists of a stochastic component, which is due to fading and which is shown in blue here. And then we have the deterministic component, which is due to path loss, which is shown in red here. And the path loss is nothing but the communication loss as the distance between the agent increases. So in Rayleigh fading, we compared the received power of the message with the sensitivity threshold. And if the received power is less than the sensitivity threshold, we drop the messages shown in this figure. In this slide, we show agents using ACBBA algorithm, and we are performing a comparison of high and low communication using Bernoulli model. We see that at high communication, each target is visited only once by the different agents. Whereas in low communication, a target may get visited multiple times due to loss of coordination. And because of this, we see that at lower communication, the simulation time, end time, takes actually longer. We now move on to the experimental setup. On the left, you see all the different parameter ranges that we use in our experiments. On the right-hand side, we have a table showing the number of experiments that we run for the different communication models. And for each communication model, the number of scenarios is set to 50. And a scenario is nothing but instance of randomly choosing a value from the parameter ranges given in the left table and then running the simulation. So once we run all the experiments for all communication models and for all scenarios, we compile all the data and then use 3 tools for visualizing and interpreting the results. The first one is the box plot. The box plot helps us to compare the algorithms by plotting the distribution of the performance metrics for each of the communication levels across the algorithms, which are highlighted in different color here. The next is the Wilcoxon sign bank test. This helps us to compare algorithms by calculating the statistical significance with respect to each performance metric for pairs of algorithms. And we have 4 levels of statistical significance as shown in the legend here. Finally is the metric trade-off plot, and this helps us to compare algorithms by plotting both the performance metrics in one plot, and in this plot only the best performing algorithms are shown. So we do these 3 plots for the Bernoulli model, Dilbert-Elliott model, and the Rayleigh fading model. And we also do it again for all these 3 models for the search and visit scenario. We encourage the reader to read our paper for the full interpretation of the results. But here's the key summary of the results. So in the visit scenario, ACBBA algorithm generally performs better across all the communication models, but certain trade-offs are seen with HIPC and PI in terms of less messages, as shown in the table towards the left. Whereas in the search and visit scenario, CBAA generally performs better at low communication, but it has a trade-off with ACBBA in terms of less distance at high communication. In conclusion, we compare 5 decentralized task allocation algorithms using 3 communication models, 2 scenarios, and 2 performance measures. And the key results are as listed in the previous slide. Our results can be used to develop meta-reasoning policies where we select the best performing algorithms at different communication levels. This work has been supported by the grant from the Air Force Research Lab. We thank AFRL for providing us this opportunity to work on this project. Here's some more information. Here's the journal link to the actual document and the corresponding information. Thank you, everyone.